joules over seconds is watts. Area, meters squared, meters, Kelvin, so that gives us the consistent units for our thermal conductivities. And so those are some of the basic ingredients you'll need to do simple calculations on conductivity. Let's see, do I want to say anything else about this? Maybe just one FYI. This is really an FYI, but some of you may be going on into sort of engineering areas, so this really is an FYI. The thermal resistance, not surprisingly, this is a conductivity. A resistance is going to be inverse to that. So thermal resistance is defined, triple equality for that, is defined as L over this kappa constant. Okay. Any of you, whoever has done anything in homes or construction or things like that, will often hear about thermal R values in terms of insulations. This is where it's defined. So the thermal resistance is inverse to the thermal conductivity, as you would expect. Yeah.
What's a triple equality?
I have kind of not done this a lot, but I kind of generally try to. Triple equality I use to define a definition. This is simply defining this thermal resistance as being this over this. So it doesn't matter. It's a definition in my notation. Okay. So I think I'm not going to just talk you through simple ways of solving the problems. As you know, now thermal energy is going to go from the warmer to the cooler object, so you can immediately identify which direction thermal energy is flowing. You can also imagine, and this is the only sort of problem I can imagine asking you, in fact, you can imagine thermal conductivity scenarios where you have two or more materials that are either in series or in parallel. And again, that's going to have interesting analogies to when we talk about electrical conduction and resistance later on. But you could imagine a couple of problems where there are the following scenarios. So I could have in my thermal baths, let's say hot and cold, like I have over in the sketch on the left side. I could imagine a couple of possible ways of setting this up. I could either make this with two, let's say, or more materials in series, something that looks like this, where these now are two different materials, 1 and 2. So you might have problems with two different materials in series, or in principle you could imagine it going the other way, so to speak, that I have several conductive pathways that are not in series but are in parallel. So it's kind of like opening up new thermal conducting pathways. And so you can easily imagine scenarios where I've got materials in series or parallel in these sorts of situations. So I think I've given you at least one problem that explores this parallel series material combinations in the homework. I'm hoping you'll find it fairly straightforward. I think I'm just going to leave it at that. So I have just 3 or 4 minutes remaining, and I do want to make use of it just because I'm already running a little bit behind. Let me just talk briefly, and I've added a little bit more material in my notes on this for you to look at. But let me just turn attention finally to coming back to radiation. I would like to just say a couple of things about that before we close. So, radiation, totally different game, and to be honest, it's more naturally fitting in electromagnetism later in the semester, but since it's definitely a mechanism of thermal energy transfer, we shouldn't overlook it totally right now. Yep. So, in particular, I want to just do an aside on radiation associated with objects in thermal equilibrium. aside, but hopefully somewhat interesting. So, quick context here. We call them hot objects. Emit electromagnetic radiation. Again, I'm going to come back to this at some length later in the semester. So, electromagnetic radiation over a range of frequencies and wavelengths. So, colors, if you will, if you're talking about visible light. So, you know this, but we'll explore it more later in the semester. And it turns out, if we look at this spectrum from objects that are in equilibrium, it's a very sort of characteristic shape. It's the so-called black body spectrum. I'm going to write this down, don't be alarmed by it. And then I'm going to show you an image of it, which may be just slightly more informative. And I'm about to run out of time, which is a little unfortunate because we're only halfway through this. Okay, so this is going to look a little bit alarming. This is the characteristics shape of electromagnetic radiation from an object which is in thermal equilibrium. It's called a black body spectrum. Let me just briefly, in the couple of remaining minutes before we close, tell you what it is. It's the amount of energy per unit frequency at a certain temperature. Okay? So when I talk about this at a certain characteristic temperature, this is that certain characteristic temperature which we can use to define the thermal equilibrium. It's going to define an energy density per unit frequency. Again, it's a bit off topic, but hopefully just bear with me for a moment. A bunch of constants, don't care what they are for now. It apparently depends on the frequency to the power of 3. Fairly strong dependence, and in fact suggests that as you go up to higher frequencies, the amount of energy goes up to the third power. That actually causes, and historically caused, some very interesting problems because this diverges, of course, and gives you an infinite energy density. Can't be true. And so you need a modifying factor, and it comes in the form of this. Again, looks pretty complicated, but let me just quickly tell you what it is. It's an exponential function which has in its numerator the frequency and in its denominator the temperature of the object. Okay? There's a lot going on in here. We're going to talk about it more later on in the semester. But let me just show you what it looks like as an example. And let me just quickly lower the light level. Okay. So, this is characteristic of so-called black body radiators. Here would be an example. Let's see. Okay, that's great. Okay, I'll make this easily bigger. So let me just go with this. What it's showing you in this image here is the spectrum to those various different colors. They're basically mapping this. The different colors are shown for different input temperatures. Okay? So what you're seeing along the bottom of that distribution is the frequency of the radiation. Again, we'll learn more about this later in the semester. But these shapes are very characteristic of so-called black body radiators. So, before I stop, let me just tell you why this is of interest. First off, it is of interest intrinsically in thermodynamics. There are situations where we may worry about thermal energy transfer via radiation in a black body context. There aren't so many things immediately in your daily life that are exactly in thermal equilibrium, but if you were, for example, to go home to your dorm room, if you have an oven in your dorm room, turn it on, let it come to some sort of temperature, and then drill a hole in the oven, okay? And then look at the spectrum of the radiation that's coming out. It will follow a distribution that looks like this, where the temperature is characterized by the equilibrium temperature inside your oven. More interestingly for us, and this is what I'll probably start with at the beginning of Thursday's class, is that our universe is to a good approximation of a black body radiator, which has a certain characteristic temperature, which I'm going to talk about at the start of Thursday's class, but just so you've heard the phrase, it has to do with the so-called cosmic microwave background radiation. It's super important. Okay, sorry I ran a couple of minutes over. I will see you guys in office hours for class on Thursday. Stay tuned for updates.